Okay, so as the last topic for our course on differential equations, we have chapter 3, which is about systems of ODEs. In particular, we're starting with 3.1, which is Introduction to Systems of ODEs. Right, so at the beginning of this course, I said that there were two types of differential equations, ordinary and partial. And the important difference was that an ordinary differential equation looks like one dependent variable upon one independent variable, whereas a partial differential equation is different. A partial differential equation has one dependent variable upon multiple independent variables. And that's how you get partial derivatives. Like I said, we're not dealing with those in this course. What we are dealing with right now is what happens if you take still one independent variable, which we're typically going to call t from now on, and then have multiple dependent variables upon that. So x, y, and z, and maybe some more variables depending on t. All right? That is the topic of the final topic of our course. Okay? So a system of ODEs is exactly what it sounds like. It's a system of equations which happen to be ODEs, for which we seek functions that satisfy all of them simultaneously. The order of the system is the highest order of all the ODEs involved. So first of all, let's write down a few definitions. Let x1 prime equal g1 of x1, x2, xn, and also t. And x2 prime is going to be g2 of x1, x2, xn, and also t. Xn prime is equal to gn of x1, x2, xn, and t. This is what we call a first order system of ODEs. The reason why it's called a first order system is because it's a system of ODEs, right? These g1 through gn are all just functions of the variables x1 through xn and t. It's a system of ODEs, and in particular, all of them are first order. Okay, so let this be a first order system of ODEs. We say that the system is linear or homogeneous or has constant coefficients. So is linear if all ODEs involved are linear. We say it is homogeneous if all ODEs involved are homogeneous. And we say it has constant coefficients. If all ODEs involved have constant coefficients. Okay. So the terminology is very simple. You just apply a term to the system, provided that that term is true for all of the constituent ODEs. All right, so here are some first-order linear homogeneous systems of ODEs with constant coefficients. You could have x prime equals 3x plus 4y plus 5z, and y prime equals x plus y plus z, and z prime equals x. It's homogeneous because all of the terms that don't have a dependent variable or a derivative of the dependent variable are zero. It's linear because we have x prime to the first equaling 3x to the first plus 4y to the first plus 5z to the first, and similarly these all are to the first as well. And it has constant coefficients because none of these things are functions of t. Well, I shouldn't say they're not functions of t, but they're constant functions of t. Okay? All right, we could have something like x prime equals x minus y and y prime equals x plus y. That's a linear homogeneous system with constant coefficients. We could have something like x1 prime equals x1 plus x2 plus x3. x2 prime equals x1 minus x2 plus x3. And x3 prime equals x1 plus x2 minus x3. That is, again, a linear homogeneous system with constant coefficients. You could have something like, now, first of all, in order to make this not homogeneous, that'll do it. If you have that, then that is no longer a homogeneous system because the first equation is not homogeneous. The first equation is not homogeneous because there is a term that does not have a dependent variable or a derivative of a dependent variable attached to it that is non-zero. Okay? Similarly here, if you put that, that's not a homogeneous system anymore. Similarly here, not a homogeneous system anymore. So what you see here is that a system is homogeneous if you don't see the t anywhere. Okay? The x, y, and z, or x1, x2, x3, or whatever you call the dependent variables, are all functions of t. But the important thing is that the independent variable does not appear. That's what makes it homogeneous. Okay? Now, how to stop this from being linear? Okay, if you want to stop it from being linear, you could do something like that. That's no longer linear. Or like, y over x there, that's no longer linear. Or something like that. That's no longer linear. Okay. And then what about if you want to have a system that doesn't have constant coefficients? Well, instead of 5 right here, maybe we'll put e to the t. And instead of just x right here, we'll put t times x. And instead of just x2 right here, we'll put e to the t times x2. So you see that in order to have linear homogeneous systems with constant coefficients, you just have to have x prime, y prime, z prime dependent on x, y, and z, and nothing else. And they need to be raised to the first power, and the coefficients need to not have t appearing in them, okay? So just like scalar ODEs, by the way, from now on, for those of you who haven't taken Calculus 3, when I have something that is an object that depends on more than one variable, I'm going to call that a vector. When I have something that depends on only one variable, I'm going to call that a scalar. So far, all of the ODEs that we've been doing in this class are scalar ODEs, whereas now we're working with vectors. And you'll see why in a minute. Okay? So just like scalar ODEs, systems of ODEs have general solutions and particular solutions, and there are initial value problems that you can solve for systems of ODEs. And some of these you already know how to do, because they're just not that hard. So let's look at an example. Let's say find the general solution of x prime equals 3x minus y, and y prime equals x. That's a linear homogeneous system of ODEs with constant coefficients. And you might be thinking about how to do this already, and it's not actually that hard. You can immediately do this even without developing any theory. The way you do it is through substitution, okay? So first thing I'm going to do is take the derivative of y prime. That's going to be y prime prime, and apparently that's x prime. X prime, according to the first equation, is 3x minus y. And then we already know that x is y prime, so this is 3y prime minus y. You move this all over to the left-hand side, and what you get here is y prime prime minus 3y prime plus y equals 0. And then that is a pretty typical scalar linear ODE that's homogeneous with constant coefficients, okay? And then you find the general solution using the characteristic equation, or Laplace transforms, or series methods, I guess, if you really want to torture yourself. I'm not going to go further than this just because we've spent about half the course on working with this type of equation, but just understand that this is the procedure, okay? So we can take this system of ODEs and substitute stuff until we get a scalar ODE. And then that scalar ODE we can solve, okay? Let's look at another example. This time I'm going to have the system x1 prime equals x2 minus x1 plus t, and x2 prime equals x2. Okay, once again, we're going to substitute stuff until we get a scalar system, or a scalar ODE, and then we'll be able to solve that. Okay, so to do this one, I'm going to take the derivative of the first equation. We're going to get x1 prime prime equals x2 prime minus x1 plus t, minus x1 prime plus 1. Now, according to the second equation, x2 prime is x2. So this becomes x1 prime prime equals x2 minus x1 prime plus 1. Now, x2, according to the first equation, is x1 prime plus x1 minus t. So this becomes x1 prime prime equals x1 prime plus x1 minus t. Then subtract off x1 prime plus 1. Then the x1 primes cancel. We have x1 prime prime equals x1 minus t plus 1, and therefore x1 prime prime minus x1 equals 1 minus t. And then that you can solve using either the method of undetermined coefficients or the method of Laplace transforms. Again, we won't spend time on that because we've already spent about half the course on that, but you get the idea. So there is a path to finding the general solution just from substituting. Okay, so these two examples illustrate that some systems of ODEs can be rephrased as scalar ODEs. That's not true for all systems of ODEs. However, the converse is true. Every scalar ODE, I should say every linear scalar ODE, can be rephrased as a system of ODEs. Not just any system, but actually a first order system. Okay, so let's talk about how to do that. So let's suppose you have an nth order scalar ODE. That looks like nth derivative of y equals f of, we have y, y prime, prime, dot, 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 y n minus first derivative, and t. This is what every nth order scalar ODE looks like, right? It's some relation involving the nth derivative of y, and making it depend on y and its derivatives and t. Okay? So we're going to rephrase this. We're going to define y1 to be y, y2 to be y prime, y3 to be y prime prime, dot, 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 yn to be y n minus first derivative. So in that case, this becomes a system, because let's take a look at this now. y1 prime, y2 prime, y3 prime, dot, 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 yn prime. We're trying to write a linear system, a first order linear system. So it has to look like this on the left-hand side. So we just have to notice here, y1 prime is y prime, which is y2. So this is y2. y2 prime is going to be y prime prime, which is y3. y3 prime is going to be third derivative of y, which is going to be y4. And so on and so forth, until we get down to yn, the n minus first derivative of y. You take the derivative of that, you get the nth derivative of y, and we already know what that is. That is this big function of y prime, dot, 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 n minus first derivative of y and t. And just like that, we now have a first order system of ODEs. Depending on what this capital F is, it might be linear, might be homogeneous, might have constant coefficients. Hard to say, depends on what F is. Okay. So let's look at some examples of how this works. Example. Rewrite the ODE as a first order system. And the one we're dealing with is x prime prime plus 3x prime plus 7x equals t, t squared. A linear, non-homogeneous ODE with constant coefficients. That means the system will be linear and have constant coefficients, but not be homogeneous. So here's how we do it. x1 we would define as x. x2 you define as x prime. And that's it. You only need as many new variables as the order of the ODE. So since this is a second order ODE, we only need 2 new variables. So we want to set this up so that it looks like x1 prime equals something and x2 prime equals something. Well, x1 prime, that would be x prime, which according to the second equation is x2. x2 prime, that's x prime prime, which according to this equation right up here, well, x prime prime is negative 3x prime minus 7x plus t squared. So therefore what we get here is negative 3 times x2 minus 7 x1 plus t squared. And that is a first order system of ODEs that is equivalent to our original scalar ODE. Okay? Let's do some more examples because these are pretty quick problems and I think they deserve talking about. Let's suppose we have y prime prime minus 4y minus y cubed equals 0. So this is a nonlinear ODE with constant coefficients. Okay? And therefore we can expect the resulting system to be nonlinear and have constant coefficients. So, define as many new variables as the order of the ODE. In this case, we're going to define y1 equals y, y2 equals y prime. So, y1 prime equals something, y2 prime equals something. y1 prime is going to be y prime, which is y2. y2 prime is going to be y prime prime. y prime prime, according to the original ODE, is 4y plus y cubed. Y is y1, so this is 4y1 plus y1 cubed. And there we have our system. Okay? Again, a first order system, nonlinear. Okay, so suppose we have something like fourth derivative of y minus second derivative of y equals 5e to the negative 3t. All right, once again, we have a fourth order ODE, so we're going to have to define 4 new variables. Start by saying y1 equals y, y2 will be y prime, y3 will be y prime prime, y4 will be third derivative of y. And we want to set this up so that we're looking at y1 prime equals something, y2 prime equals something, y3 prime equals something, and y4 prime equals something. Well, y1 prime is y prime, which is y2. y2 prime is y prime prime, which is y3. y3 prime is y third derivative, which is y4. And then y4 prime, well, that'd be the fourth derivative of y, which according to this first equation, the fourth derivative of y is y prime prime plus 5e to the negative 3t. Therefore, what we get here is y3 plus 5e to the negative 3t. And there you have a first order linear non-homogeneous system. And let's try one with non-constant coefficients. So suppose you have t squared x prime prime plus tx prime plus t squared minus 1 x equals 0. A linear homogeneous ODE with non-constant coefficients. Well, once again, we're going to need as many new variables as the order of the ODE. The order of the ODE is 2. So define x1 to be x, x2 to be x prime. That's all you'll need. Okay, so x1 prime equals something, x2 prime equals something. x1 prime is going to be x prime, which is apparently x2. x2 prime, well, in order to figure that out, we need to figure out x prime prime, which is not so hard. We just need to rewrite this initial ODE. First of all, we can write t squared x prime prime equals negative t x prime minus t squared minus 1 x. Divide both sides by t squared, you get x prime prime equals negative 1 over t x prime minus t squared minus 1 over t squared times x. And then this becomes negative 1 over t times x prime is x2 minus t squared minus 1 over t times x, which is x1. And there you have it, a linear homogeneous system without constant coefficients. Okay. So that's pretty much all there is in section 3.1. The important thing to take away from this is that all of the ODEs that we've been doing so far, based on the examples that we were just doing, they can all be rephrased as systems of ODEs. And moreover, some systems of ODEs are not translations of scalar ODEs, which means that we're dealing with, when we deal with systems of ODEs, we're dealing with a broader problem than we were before. Before we were just thinking about, well, scalar ODEs. Now we're thinking about not just scalar ODEs, but also systems that can't be defined by scalar ODEs. Okay? So, that's it for 3.1. Let's move on to 3.2. Inevitably, when you talk about systems in math, at least after high school, you're going to have to talk about matrices. So 3.2 is about matrices and linear systems. Okay, so first of all, what is a matrix? Well, hopefully you've experienced these things at some point in your life. A matrix is an array of, well, a rectangular array of mathematical objects. So, let's make this easier. 1, 2, 4, negative 1, 0, pi. This, for example, is a matrix. Okay? And the whole idea of two matrices being equal just means that each corresponding entry is equal. So these matrices are equal. These matrices are not equal. Okay? So it's just this array of numbers arranged in a rectangle that, you know, in order to consider them equal, they just have to have the same corresponding coefficients. Or not coefficients, entries. Okay. So, in my notes, I talk about the different operations you can do on matrices, which we'll need. Scalar multiplication, addition, and multiplication of matrices. In my notes, I talk about it for arbitrarily large matrices, but for us, we're pretty much only going to be concerned with 2 by 2 matrices. So let's only focus on that for now. So scalar multiplication. Scalar multiplication is like this. Let's say S be a scalar. And by scalar, I mean a real or complex number. If I want to multiply this scalar by a matrix, let's call it A, B, C, D, all I have to do is multiply each entry by the scalar. Easy as that. So for example, 2 times the matrix 1, 7, -1, -2. So example, this is the matrix 2, 14, -2, -4. Easy enough, right? That's how scalar multiplication of matrices works. Okay. Now, how about addition of matrices? If you have two matrices, call them A1, B1, C1, D1, and you want to add that to another matrix, A2, B2, C2, D2, all you have to do is just add up the corresponding entries. So A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2. As an example, if you have the matrix 1, 0, -1, -1, and you want to add that to the matrix 2, 2, 1, 6, I'm just pulling these numbers out of thin air. There's no reason I have to select these numbers, of course. This is just an example. You just add 1 plus 2, that's 3. 0 plus 2, that's 2. -1 plus 1, that's 0. -1 plus 6, that's 5. And there you have it. Okay. Now, multiplication of matrices is significantly more complicated. In order to multiply two matrices together, we're going to have to take a minute to talk about vectors. Specifically, for those of you who have not taken Calculus 3, we need to talk about dot products. Okay, so first of all, definition. A column vector is a matrix with one column. If you've taken Calculus 3, then you know that there is a more geometric interpretation to what a vector actually is, but for us, we'll just say a column vector is a matrix with one column. A row vector is a matrix with one row. The zero vector I should say the zero column vector is the matrix. We denote it by 0 with an arrow over it. It's just a column of all zeros. However many variables you have, that's how many zeros there are. Okay, now let's talk about dot products. So, let me actually move my tablet over like this. Definition. Let U be 1 by n row vector, which means that it has one row and n many columns, so n many entries. And let V be an n by 1 column vector. So that means that it has n rows and 1 column, n many entries. So the same number of entries. So U vector is going to look like an array of scalars, a1, a2, a3, dot, 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 an. And V vector is going to look like also an array of scalars, but they might be different scalars, b1, b2, dot, 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 bn. The product, or dot product, of U and V is U vector dot V vector equals, okay, this looks like a1, a2, dot, 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 an multiplied by b1, b2, dot, 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 bn. All you have to do is multiply together the corresponding entries and then add up the products. So this is a1, b1 plus a2, b2 plus dot, dot, dot plus an, bn. Okay. So, examples. Let's determine the product of the row vector negative 5, 6 and the column vector 2, negative 1. Okay, easy enough. Multiply negative 5 times 2, you get negative 10. Multiply 6 by negative 1, you get negative 6. Add these together, you get negative 16. That is the dot product. As you can see, the dot product of two vectors, a row vector with a column vector, is a scalar. Okay? So now we can finally define multiplication of two matrices. If you have A, B, C, D, and you're multiplying that by E, F, G, H, here's how you do it. This is the first row, first column. So what you're going to do is take the first row of this matrix on the left, which we'll call A, and this one on the right we'll call B. The first row of A times the first column of B, dot product. So what that comes out to be is A times E plus B times G. Then you have the second column of the first row. So you're going to dot product the first row of A with the second column of B. So what this gives us is AF plus BH. In the second row, first column, the entry is going to be the dot product of the second row of A with the first column of B. So that's going to be CE plus DG. And then in the second row, second column, we're going to have the second row of A dot product the second column of B. So CF plus DH. And that is how you multiply together two 2x2 matrices. Okay? Like I said, my notes have more general examples, or explanations, I should say, with arbitrarily large matrices, but for the most part we'll only need 2x2s. And this method of just taking the dot product of rows and columns does extend to larger matrices. Okay, so let's look at an example of taking the product of two matrices. So this is multiplication of matrices. All right. I'm going to take 2, 0, 2, negative 1, and I'm going to multiply it by negative 1, negative 2, negative 2, negative 1. The result will be another 2x2 matrix. The first row, first column entry is going to be first row of A dot first column of B. So negative 2 plus 0 is negative 2. Then the first row, second column of the product is going to be first row of A dot second column of B. So negative 4 plus 0 is negative 4. The second row, first column of the product is going to be the second row of A times the first column of B. So negative 2 plus 2 is 0. And the second row, second column of the product is going to be the second row of A times the second column of B. So negative 4 plus 1 is negative 3. And that is our product. Okay. So there's just one thing left to say. It's about determinants. So we've already discussed determinants in the context of Wronskians. In general, we can talk about determinants of any square matrix. By square matrix, I mean it has the same number of rows and columns. So like this, we can take the determinant of this 2x2 matrix. It's going to be, oh, by the way, the vertical lines mean determinant, whereas the parentheses just mean matrix. Some people also write square brackets here. That's the same thing. It just means matrix. Whereas the vertical lines mean determinant. Anyway, the determinant of a 2 by 2 matrix is just AD minus BC. The determinant of a 3 by 3 matrix, well, we computed those when we did the Wronskian. Let me just remind you, if you have A, B, C, D, E, F, G, H, I, the determinant is A times the determinant of E, F, H, I minus B times the determinant of D, F, G, I plus C times the determinant of D, E, G, H. And there are 4 by 4 determinants and 5 by 5 determinants and 11,000 by 11,000 determinants too. But we're just going to need 2 by 2 and 3 by 3. In fact, probably just 2 by 2 for going forward. So I want to consider the following question. If you have a linear system of equations, they don't have to be differential equations, just any type of equations whatsoever. Let's say they're all equal to 0. So this is what we call a homogeneous system. You can write this as a single matrix equation. You can write this as the matrix equation A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, dot, 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 AN1, dot, 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 AN2, dot, 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 ANN, dot, 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 dot. Multiply this by x1, x2, dot, 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 xn as a column vector, and that's equal to the 0 vector. This is often significantly easier to work with because it's just one equation as opposed to n many. Okay? Now, let's call this A, and let's call this vector x. So what we're looking at here is an equation of the form ax vector equals the 0 vector. So I have a question. Does ax vector equal the 0 vector have a solution? The answer is yes. It always has a solution. Just take x1, x2, x3, x4, x5, x6, x7, xn to be zeros. In other words, take x to be the 0 vector, and then a times the 0 vector will end up being the 0 vector. So, yes. Take x vector to be the 0 vector. Okay, so that's not very interesting. That's what we call the trivial solution of that equation. The question is whether others exist. Do other solutions exist? Where again, we have A and we're solving for x. Okay. So the answer to this is given by the following theorem, which is from linear algebra, and it is crucial to our theory. I'm not going to prove it because, again, that's for a linear algebra class, but let's just state it. Let A be an n by n matrix. So n rows, n columns. The matrix equation Ax vector equals the 0 vector has a non-trivial solution. By non-trivial, I mean not the 0 vector. So this is the trivial solution. So this has a non-trivial solution if and only if the determinant of A is not 0. Okay? So therefore, I'm getting ahead of myself. We'll see in future lectures how this is important. For right now, just keep it in mind that we're going to be very concerned with equations of this form, and just know that they have a non-trivial solution if and only if the determinant of A is non-zero. Okay? Anyway, that's all for today. See you in the next one.